I hope everybody can hear me. If not, then please let the organizer. So thank you for inviting me, and thank you for watching me online and coming. So I will talk about an axiomatization paper in financial networks. It's a joint work with Jean-Jacques Herings, who also visits me, usually in autumn. But this year he will also come to other conference organized by Peter, but I will also come in summer. And so this is just the outline as usual. Maybe it's better to start what we are talking about in financial networks. So we talk about bankruptcies of banks, companies, organizations, and individuals. And what is a challenge if you have circles? So an agent has a liability to another agent, and that's I will node by node, and then to A to B, B to C, and C to A. And then you have a circle, and then it's not obvious what will happen, what are the possible equilibrium, there is one equilibrium or not. And it could be that one entity, I will call it entity, will go bankrupt because the other agent is not paying, and then it's a contagion. So if all the claims would have been paid to this agent, nothing would have happened. But the problem is that there is a contagion. And here I just mentioned that you could use similar models with some adjustments to supply chains, international student exchange, IT servers, processing jobs, time banks, and maybe also to allocation of COVID-19 vaccines. But this is what I actually wanted to talk about. So here are some of my papers in financial networks. Two prominent papers are in management science, but I also cite here a paper in Sigma and alkalmazat matematikai lapok. And the whole my research started with the following problem that is like back to 1982 with O'Neill. There is an estate, maybe a person deceased, and then it has some liabilities to some persons, like have to pay 2, 3, 5. But right now the total amount available is, let's say, 7. And the question is how to allocate the 7 to the claimants having claims 2, 3, and 5. And you can think of many possibilities, maybe proportionally, but maybe you want to give everybody the same. There could be some applications, but at most their claims, or maybe everybody should suffer the same loss and this kind of thing. And it is an old literature. And when we jumped in is the first paper, when we started to treat also this estate, so to say, or the one who has all the liabilities as a player. And that in that way we introduced a new cooperative game. It turned out nobody was treating this as a player. And then we defined the payoffs for all the coalitions, all the subsets of the players. And then, of course, it was just the first step to go towards a financial network when you also have liabilities everywhere, and then you could have circles. And then we were studying decentralized clearing that I remember I was presenting here like 5 or 8 years ago, when you have a smallest unit of account and you just look at what happens that everybody pay under some conditions. And it turned out that it's a centralized clearing mechanism, and you have to collect all the information. But here you don't have to collect all the information. And then the third one, which is mostly related to what I am going to talk about today, is what happens when everybody is paying proportionally, but how much you can pay depends on how much you receive. And that's why I am listing here, if I can use it, yes, that in financial networks, maybe I should just move it a little bit. This can be solutions could have solutions to a systems of equations where you want to determine at the end how much who is willing to, how much they will pay at the end, or it's a set of fixed points, or it's also can be seen as solutions to linear programming problems when you have proportional rules. But in general, in paper 4, we show that for all the other possibilities and maybe even more, also to a priority rule that maybe first you want to pay to the first agent because it has a higher priority, and then to the second if there is still some left. You can calculate all those payments using integer linear programming. Okay, but I forgot to finish this one. So the third one is the most related to what I will talk about. And there we have some axioms, some properties, which characterize the solution to this system of equations or linear programming problems. So if you want to satisfy certain properties, this can only be done with the proportional. And then we also had issues with the uniqueness. And no, I just turned to this pairwise netting. But before that, some more literature on the proportional without pairwise netting. So it started with the paper by Eisenberg and No. And there are many extensions. But actually here we just deal with the basic model. So there is no bankruptcy cost and other things, just normal liabilities, no priority structures, whatever, no credit default swap like in this paper, and still there are very interesting questions to be answered. Of course, it was also studied how the default is happening in the network and how it depends on the network topology. It's also related to measuring systemic risk. You could somehow select those financial institutions which are important, and then maybe you want to have a higher capital requirement for now. And there are very good surveys of this literature. But now I want to talk about pairwise netting and then the proportional rule. So what is pairwise netting? That I have A has a liability of 5 to B, and B has a liability of 3 to A, and then let's net it. Then A just pays, A just has a liability of 2 to B. It seems to be straightforward. Why not do it? The problem is that what happens if B goes bankrupt? And there are also other players. And then B is not paying everything, for instance, to C, but with this netting, we assume that B is paying all 100% to A. So it has some effects. And by the way, it's also called bilateral netting or bilateral compression. And it's by default applied to over-the-counter derivative trades. So trades which are not through a stock exchange. And they have to sign an agreement that then if there are situations like this, then it will be automatically netted. But of course, they take into account when they do these trades. And there are many related papers here. And I will show in a minute or maybe 20 minutes that it could be that agents have strictly positive initial endowments. So from general equilibrium theory, we use this word initial endowment. It's just the initial money available. So everybody has a positive initial money, like 1 million euros or whatever. And everybody has a higher claim than liability, like here, B has a higher claim, 5, than liability. And still, player B could go bankrupt with this pairwise netting, which is bad, with the proportional, sorry. So this is just simple proportional. So without pairwise netting, B could go bankrupt. But with pairwise netting, of course, B will just have claims at the end. And in general, that's a good point for pairwise netting. But the technical and I would say legal details are very complicated. So there is a so-called credit support annex, and to really do this netting, maybe you have to put aside some collateral, some very liquid, to come back to the liquidity conference that I will also mention, very liquid security. But it could be that there is a new central clearing counterparty who does this netting, but may go bankrupt. And then there is a huge literature on this central clearing, and there is a nice survey on the economics of clearing. So this is really good for economists if you are interested in. And I just figured that one of the authors just accepted our invitation. So, but yeah, here it is. Albert Mengfeld will be one of the keynote speakers in the conference we were mentioning. So it will be 14th, 15th November, and the submission deadline, it will be somewhere in June. Okay, so now to finish the introduction, what is the main result? We axiomatize the pairwise netting proportional rule, which means first you do bilateral or pairwise netting, and then everybody pays proportionally depending on how much you receive. So you solve this system of proportions. And you can come up with any solution if it satisfies the axioms of net impartiality and invariance to mitosis.
What is mitosis?
Yes, I will tell you what it is. So mitosis is the word we invented for a special kind of manipulation that the players split, but split evenly. Like it's not correct, of course, because you could split in this model. You could create 3 more companies or whatever, but you have to do it in such a way that you just split the claims and liabilities evenly, because it could be tempting that you just take the claims to one firm and put the liabilities to the other, but that's kind of illegal, and that's not what we allow. So no manipulations possible by this kind of we were calling it non-manipulation by identical agents. That was the original word, but one referee thought it would be better to change it to invariance to mitosis. Net impartiality means that if after netting A has to pay the same to B and maybe to C, then A should pay the same. So if A has the same liability to B and C after netting, which is of course then kind of already incorporates this kind of netting idea, but still it's not obvious how to get it, then the payment should be the same, but not necessarily 100%. So it could be that just 50% or whatever. And the other axioms are just basic axioms. Claims boundedness, you pay at most as much as your liabilities. Limited liability, the final equity or the final balance of the agents should be non-negative. Priority of creditors, if you do not pay all your liabilities, your final account should be 0. And continuity, if you slightly change the problem, the final payments should also just slightly change. Question.
The 2 questions that do not understand why this pairwise, how this pairwise liabilities work. For example, assume that at the first period, agent A lends $5 to B, and instead in the second period, the agent B lends $3 back instead of repaying the original. I do not know why these things appear and how frequent they are.
Yes. So it goes back to this finance applications, which was maybe somewhere here, that actually it can be many derivatives that they are trading at the same time. So I agree that I will buy Apple in 1 year at $500 or whatever. I don't know the current price, but I will know it after teaching the course soon. And you can enter into many trades like that. And then these trades are always updated. So these are not only loans, maybe I was not precise, but all kinds of financial contracts which have a value. And then they have many contracts, and that's why they already signed this, that they will just net and check, okay, in this deal, I owe you 5, but on other deal, which is completely different, you owe me 2 and things like that.
Mhm.
So what did you have another?
Yes, and how frequent they are.
Oh, frequent? Yeah, it's quite frequent in these finance applications. And actually, there are also firms who are seeking and try to find not only bilateral but multilateral cycles and offering this to reduce the so-called gross positions, because that's always risky because it could change. You see that I was also mentioning it with the legal things that it's better to have just these 2, because then both numbers are reused and not much risk. So that's why they like it. And
One company is Trioptima.
Trioptima,
So
that
if
is,
you Google it, they clear $3 every night.
yes.
Maybe out of the box. In reality, there is a market for the claims. So there is a secondary market. And if you are,
Yes.
if you are putting that into this type of framework, we are totally Israel. So because of this, obviously this type of market assessment, market pricing will somewhat react to these issues. So this is a reality in the finance, it's reality in all the and so on and so on. So, but as I see, you do not consider this type of.
That we don't consider, but no, it turns to my mind that it also have applications to the firms when you have these commercial loans that I send you some product that you can pay later. And it turned out that it's not only in Romania, but Peter mentioned it, but also in Croatia now they are doing this. That firms can send their bills that I expect some payment from this, and there are circles, and then there is a ministry who is doing this netting, and then everybody is kind of better off. So that's how they try to solve this. Yeah, but that's a different application that maybe I should emphasize more. Okay, so the other axioms are just basic axioms. And yeah, maybe I should also tell that the project started that you can see the paper like you just did it pairwise netting. So we have a previous paper in management science where we axiomatized the proportional rule with the same axioms, but the net was not there. And then it could seem that it's very easy, and that was also our first guess. But it turned out that we had to use all the other papers to really solve it, and I will try to show you some things. Like we had to use this programming approach when it is unique. But I will just show you some flavors how we did it, and the paper is still in the reviewing process. So now I will go to the notation, but I will show you some examples. Better looking examples like this. So we have the collection of non-empty subsets of all the natural numbers, because here the number of agents could change. The set of agents is denoted by n, and then z, which is a strictly positive real number, is the endowment of the agents. This is what I was mentioning as the initial available perfectly liquid money. You can also say it's all tangible and intangible assets, but of course not the claims and liabilities. Then you have a liability matrix. So this network, behind this network, there is a liability matrix where Lij, so row I, column J, is the liability of agent I towards agent J. Of course, along the diagonal you have zeros, but you could have that you have liability between liability from A to B and B to A. And then there is some extra notation for all the matrices with such properties that they have non-negatives everywhere, non-negative real numbers and zeros along the diagonal, and the financial network is F. And then, given a financial network, so this is the initial problem. You have the set of agents, their initial endowments, and liability matrix. You want to get a payment matrix. That's the result of the clearing, which tells you at the end how much agent I is paying to agent J. And given that, you can calculate the asset value of an agent, which is the initial endowment plus what agent receives from the others. And then if you also subtract what agent I pays to the others, then you get the equity. And this is the final balance that we want to have non-negative. A bankruptcy rule is what we are looking for in general. It assigns a payment matrix to a financial network to all initial problems. And if you just have a claims problem that I started here, that there is just one agent who has liabilities, and then its initial endowment is called estate. And that's how we want to, this is 7 is the estate that we want to somehow divide to the claimants. And you can do it proportionally. You just calculate for all claimants J, their relative claims, 2/10, 3/10, 5/10, and multiply it by the 7, and then you get the proportional rule, which was studied proportional division rule. So now we make the distinction division rule when you have just one agent having all the liabilities, and bankruptcy rule when you have a network. So that's just our terminology. And then for financial networks, you have to calculate the relative liabilities, the whole matrix, like agent 1 has this relative liability row and agent 2 and so on. And then you have to solve the system of equations where the payment from I to J is at most is the lowest number. At most, you pay your liability from I to J, but otherwise, it could be that you cannot pay it because what you initially started with and plus what you receive, that's your total estate, which is now endogenous in this model. It depends on how much you receive, and that's why you have to solve a system of equation. But then you have this liability ratio that I owes to J 20% of its liabilities, and then I pays 20% of its endowment to J. And then you can see that this is a system of equations, and it may have multiple solutions. We also have a paper where we show conditions under which it's unique. But for instance, if all the initial endowments are strictly positive, then it just has one solution. And here is the example. So now we just do the proportional clearing. We have 3 agents, and the initial endowments are 10 million euros, 1 and 40. And here is the liability matrix. So agent 1 has a liability of 400 to agent 2 and 40 to agent 3. And agent 2 has a liability of 360 to agent 1. So now you could do this netting, but let's not do that yet. First, let's see what happens without netting. Without netting, I claim that this is the unique solution of the problem, and that you pay proportionally to everybody. Let's see why, and then it's easy to check. So agent 1 started with 10, and yeah, first maybe we can check the payment ratio. So agent 1 pays 80% to everybody, right? So that's okay. Agent 2 pays 95%, and agent 3 pays 100%. So the payments are proportional. And then agent 2 pays to agent 1 342, and added to 10, that will be the endogenous estate value of agent 1. So agent 1 has 352, And indeed, 320 plus 32 is 352. So everything what is received by agent 1 is paid out to the other agents. Agent 1 cannot pay all the liabilities, it just pays 80% and ends up with a zero balance, zero equity. So agent 1 defaults in this model. Agent 2 also defaults, but from contagion, because had agent 1 paid all the 400, then from 401, agent 1 could have paid the 380 in total. So the default of agent 2 is by contagion. And the problem is that agent 2 has a higher claim than liability, both to agent 1, because agent 1 should pay or has a liability of 400 to agent 1, but agent 1 just 360, and also to agent 3. So agent 2 has a liability of 20 to 3, but a claim of 40 from 3. But still, agent 2 defaults. So if we had this netting, no problem would have happened. And the problem is that, as you can see, the netting would have been 360, but agent 1 pays less than that, just 320 to agent 2, and that's why we have this problem. And we show, which is quite trivial, but still it's interesting that after netting, this cannot happen, that an agent like agent 2 defaults. So what is this netting formally? Let L lower by bar ij denote the minimum between Lij and Lji. So in this case, just this 360, and here it's the 20. So that's the nettable liability. And after subtracting the nettable liability, we get the netted liability between agents I and J. And then the pairwise netting proportional rule is that first you have to pay the netting, but I will show you the same in an example. And then after netting, what is left, you run the proportional. So maybe it's better to show you here. So the same problem. And then, as we saw here, the lowest number is 360, so we can just cancel it. Here it's 20. But you cannot just cancel it. You have to pay it to, at the end, really pay the 360 and 400. So this L over bar, the netting amounts automatically enter to the payment matrix. And then, if you subtract this, from the initial problem, then you get this L hat, which is what is the remaining liabilities, like here, the 2. And then it's an easy problem. Agent 1 has a liability of 40, what is left at 40 and 20. So agent 1 will not receive nothing from agent 3, so it's easy to solve. You just have to allocate 10 in a proportional way, the same to agent 2 and 3, so it's 5, 5. And agent 3 pays 20. So these are the proportional payments after netting. And then netting plus proportional payments after netting together is the total payments after applying the pairwise netting proportional rule. So if you sum up the respective numbers, then what you get, it's 365, 360, and so on. And then you get, of course, a different asset value, which is higher for agent 2, 406. And then agent 2 ends up with an equity of 26. So after this pairwise netting, agent 2 will not go bankrupt. And here we could see that agent 1 goes bankrupt. That's what I was trying to say here. And by going bankrupt originally, it's not even paying the 360. But now when you say, okay, let's do pairwise netting, then this bankrupt agent will pay the 360, 100%, and maybe some part of the remaining. And that's better for this agent. Okay, now I just define the axioms and maybe show some tricks of the proof. So what is net impartiality? It means that for agent I, if after netting, the netted liabilities to both J and K are the same, then agent I should pay the same on top of netting. So that's what we saw here actually. So after netting, agent 1 has a netted liability of 40, goes to 2 and 3. So after netting, of course, in this example, agent 1 pays the same to them. And here comes the formal definition of this invariance to mitosis. When you are splitting, but actually it also applies to merging. So you can also merge the same agents. For splitting, a practical application is if somebody gets divorced and then you split everything proportionally. But otherwise, it's just an axiom in the system to guarantee non-manipulability. So what you do is that equal split of the endowment, claims, and liabilities of the agents. So there is an agent J, and then you know you have a new set of agents K. So agent J splits to J union K, and then let's see what happens. And what should happen is that what agent J originally paid to I in the original network, and now we end up in this F prime new network, should be the same if you look at the clones. It's also called clones, by the way, and manipulation by clones. Maybe it's even better. So you have agent J, and then there are just some clones, and it's the set of K. So now it's has 3 clones, so in total it's 4. So what originally agent J was paying to I should be the same as after this cloning and splitting, they in total pay to I, and it's the same for receiving payments. And the other agents shouldn't be affected. So to sum up, it means that split of an agent into multiple but identical agents shouldn't affect the payment matrix. And you can also read it the way back that merging identical agents shouldn't affect the payment matrix. And that's what I will show here. And I also define a new rule at the pairwise netting, and it cannot be seen, but it's called pairwise netting constraint equal loss. So let's see what it is. And that you see that in principle, it's not only the proportional rule that could be used. So we have 4 agents, and we can see that 3 and 4 are identical. They have the same initial endowments, and they have the same liabilities, agent 1. And we want to merge those. But let's see, before merging, what is happening. Let's do pairwise netting. Then 3 has a liability of 1 to 1, and 1 has a liability of 9 to 3. So along this, you can always net. I don't even write that. I just write the netted liability matrix, and it's quite symmetric. So agent 1 has an initial endowment of 80 millions and has to pay 3 times 8, 24 millions. And now it's the same as the proportional, the solution, but I want to apply the equal loss, which will be different in the next slide. So everybody should suffer the same loss. Then everybody suffers 2 million euros loss. Everybody gets 2 million euros less in this example. That's That's the solution of rationing 18 million euros to those three claimants. And we also had this netted amounts, which was 1 and 1. So if you add that, what happens is that agent 1 will go bankrupt, agent 2 ends up 8, and 3 and 4, 7. So by the way, we are always just reallocating the sum of the initial endowments. You can also see that program. It's 22 in total. And now maybe the next slide will make it clear what I mean by equal loss. So let's merge 2 and 3 and 4. So what was happening? Both 3 and 4 suffered the loss of 2. And now we are thinking about, do they have an incentive to merge if everybody suffers the same loss? And of course, because then they are just one player. And then what you see is that this is the new problem. So they merge the sum of the endowments and the liabilities. And now the new netted liability matrix is 8 and 16. And here you can see that it's not proportional now. So in total, you have 24, which is 6 times higher than 18. So a loss of 6 should be allocated evenly. And that means you have to subtract 3 from those 8 and 16. But now what happens is previously we had 3 players with a loss of 2. Well, now we have 2 players with a loss of 3 both. So those second 2 players are gaining, because previously the total final equity was 14 and now it's 15. So what I showed is that the pairwise netting constraint equal loss rule doesn't satisfy the invariance to mitosis, because players have an incentive to merge. But the pairwise netting proportional rule satisfies this. Now, just to finish with the other basic axioms, claims boundedness means that you just pay at most as much as your liabilities. Limited liability means that the final equity for all the agents should be non-negative. And priority of creditors means that if the payment row for any agent is less than the liability, which means that it can be less for any element. So if there is at least for an agent, not all liabilities are paid, then its equity should be 0. And we have continuity, that this function is continuous. And then the axiomatization is that we show that the pairwise netting proportional rule satisfies these axioms I was showing. And the other side is more difficult. To start with any bankruptcy rule, assume the axioms and show that it can only be the pairwise netting proportional rule. And for that, I show you some 2 minutes from the proof. So what turned out to be difficult is that with this system of equations after netting, I already showed you. But after netting, you have to pay proportionally. So at most the liabilities, or if your endogenous asset value is lower, really. But in general, this netted payment matrix is, we cannot say it's non-negative. What we can only say is that it's at least as much as the opposite of the initial, is the opposite of the netted liabilities. And let me go back to the example to show you why. Yes, so already here, we start with any bankruptcy rule that we can imagine, and it could also be the proportional rule. And here you can see that this is the total payment matrix. And now we are looking for, we would like to split it such that it's the netted payments plus some extra payments, which are after that. And here we can see that the netted payments are 360, but the total payments is 320. So on top of netting, the payment is negative. And that's what is causing complications in the proof. That it could be that on top of netting, you pay a negative amount, and at the end you pay a non-negative amount. But of course, this on top of netting can be at most as much in this example as 360. So it could be that, for instance, this agent is paying 0 at the end, which is 360 plus minus 360. So that's why we have to relax this problem, and then we have to use all the tricks that are in the other papers, like looking at the lattice, and the most difficult part is to show that this system of equations has a unique solution, which is obvious that one solution is the pairwise netting proportional rule, because that's what is essentially here, that after pairwise netting you do proportionally. But to show that it's really unique, we have to use this technique of having a financial network where you have arrows corresponding to liabilities. Here we don't specify what kind of number it is, it doesn't matter, it's just a network. So agent 1 has some liability to 7, 7 to 8, and so on. And then you have these components, which is a standard tool in network theory. It's called strongly connected components, and these are these rectangles with the property that any two distinct agents are in it, are connected. Connected in the way that you can go from 2 to 4, 4 to 5, anywhere, and it's maximal. So because it could be that you just take this circle, but then you have to have it maximal, and then it's unique how you define these rectangles, and then you partition agents to these sets, and then from these circles you can get a directed graph just by linking the rectangles if there is a link between them. So you link this to this, and here you just have one link. So then there are no circles. And I also wanted to say something. Yeah, so the essence is that you have to do an induction along these rectangles, and you can always know that you can just go O4 only is affected by players in O2 and this kind of thing. So you go from O1, 2, 3, 4, 5, and then you can do this induction kind of argument. So that's what's essentially here. And that's my talk. So, but 2 more minutes. So we show that we have these axioms: net impartiality, invariance to mitosis, claims boundedness, limited liability, priority of creditors, and continuity. We show that the pairwise netting proportional rule, which is that you do just pairwise netting, not more, like multilateral, and then you apply the proportional rule, satisfies all those axioms. And we also show that if you start with any rule satisfying these axioms, it can only be the pairwise netting proportional rule. Then we have an axiomatization, but we also have to show that the axioms are independent. It could be that these 5 axioms imply the first one, but if we show an example which satisfies these 5 but doesn't satisfy the first one, then it's not. And that's what you can see here. So the proportional rule doesn't satisfy this. Then we have the pairwise netting constraint equal as I showed you, not satisfying invariance to mitosis. You could have imagine double liabilities that would violate claims boundedness. All liabilities are paid. That's also an easy rule. You pay everything. The problem is that you would end up with negative amounts. Then you can also say common liabilities are paid, although I don't remember what I mean by this. Maybe that's a typo, but it should be easy, but no, I do not know. What I know is that priority to irrational claims, but it's in the mathematical sense. It's not high claims, but claims of irrational numbers. So to have this continuity trick, And yes, we allow for liabilities of square root of 2, even though it seems impossible. But if you have a liability of square root of 2, and then you have a liability of 2 point or whatever, 1.42, whatever, 4142, then first you have to pay the irrational liability and then go for the rational. And then it will not satisfy continuity, because if you go on with this 1.41 whatever, then at the end you violate this. So that's it. Thank you for your attention, and I'm looking forward to your questions.
Let me go back to the statement of the theorem,
Yes.
the main theorem. Okay, so would you say that this rule has to satisfy 6 properties?
Mhm.
Some of them are more technical than others, for example, this irrational stuff.
The irrational stuff is for the counter example. Related to that is continuity, which you might call technical, maybe not,
Right.
because if you change slightly the problem, the final solution.
So can you bundle together into one intuition, right? Why all the main properties are needed for this proportional rule? Or it just can be done without, it goes through a series of examples and
Yeah.
then you get a certain insights.
The intuition, maybe I can show you the counter example, because here is also, these are counter examples. So if you have just 5, then I can show you an example which is not satisfying the 6th one. So that's also kind of a proof.
So this is a genuine result of combining
So, yeah, so
lots of considerations through counter examples and examples, but there's no one major insight behind.
yeah, so but usually what you do is you try to come up with some axioms and see if it works or not. I'm not claiming that there is no other possibility. And what I am claiming is that maybe these axioms are quite natural in a sense, although net impartiality, I confess, it's close to this netting, but still it's not obvious to do it. Peter,
So if you compare the first two, you said that in your paper you also characterize the proportional. So I'm just wondering what is the extra property that proportional has, and this yours doesn't have.
yeah, so that's simply, as I said, changing the net impartiality to impartiality. So that means that if you have the same liabilities to A and B, you should pay them the same. And here you say after netting, if you have the same liabilities, you should pay them the same. So it seems trivial, but as I showed,
So that's the only difference.
That's the
All
only-
the other.
yeah, that's the only difference. That's why it could seem difficult. It seems easy, but indeed we really had to modify many things. But of course, we use the structure of the proof, but still it turned out to be quite complicated. You?
I have a general question that you mentioned that you talked quite a lot about the invariance to mitosis, but does it have also a real life relevance, or it's just a mathematical property?
It's a mathematical property, but I was trying to joke with the divorce. So if you and wife get divorced, then you share under some rules the liabilities and the claims evenly, and then it shouldn't affect your total situation.
Can you generalize for cases where for mergers where the different agents are not the same?
For not the same, no. So in that sense, we require nothing in that case. In the previous paper, we have an impossibility result, actually, that if you allow for not same agents, so just non-manipulability in general, then there is no rule which satisfies claims boundedness, limited, and maybe limited liability. So it's so strong that you just cannot satisfy it, because what I was saying, that then you would split the claims to one and the liabilities to the other.
Even if they have the same, like, okay, you have one guy and the other has like 3 times as much.
Oh, if it's proportional, that's also okay, I guess.
Okay.
Yeah. So, but then actually we were thinking about that. So that could also be the case, that instead of invariance to mitosis, we change it to invariance to proportional mitosis, but then it's very close to the proportional rule in a sense, and then you could criticize it. But if you like, you can do that. So you can change that to proportional.
Maybe wrong question. Any intuition how you could extend this to multilateral?
To multilateral, that's a difficult problem. Although we have some ideas, which I don't know if I can tell you or not.
You can tell us, but I'm freelance.
Yeah, but, oh, please don't record it. This is the most important part of the recording. Yeah, so with the multilateral netting, but Peter maybe knows more about it. The problem is that it's not unique how you net it, because you could have a circle here and a circle there, and then this intersecting agent, you could do it in different ways. But maybe one possibility, which is also interesting, would be if you introduce a central clearing counterparty, taking over all the claims and liabilities, and then maybe you can do something.
Because that's a unique solution. Like
That's
well-defined.
That's a well-defined. Yes. Yes.
If there are no questions, thank you very much.
Thank you.